Welcome on today's presentation. We will discuss about the visual perception of humanoid robots. We will start with some general introduction. Yes. We will discuss basic terms and concepts. Then we will discuss the principles. We will show some the examples how the robots perform as visual perception. Whether this perception is satisfactory or do we need other sensors to create a complete image of the world. We will briefly discuss advancement of analog robots of the visual perception. So, the first, what is a humanoid? Humanoid is, let's say, the robot which somehow resembles the person. There is some kind of humanoids, some of them you definitely know. And humanoids have some features which distinguish it from the different kind of robots. So we can consider the humanoid robot as one kind of typically embodied AI. There are, of course, other robots than just humanoid. There are industrial robots. There are robots like autonomous vehicles and so on. So there is lots of kind of robots. Definitely, it must be autonomous system. And what is important for perception and sensing? All sensors are on the body. No on the other places. For example, this is not true for the industrial robots. They have cameras on the other places. They are not directly connected to the body. And this also means that the sensors are moving together with the robots, which impose some burdens and problems for the sensing the robot when the robot is on the move. And usually, the humanoid robots are collaborative. It's not strict rule, but usually the humanoid robot should be cooperative with other robots or other persons or other entities. One of the examples of the autonomous robot, which is collaborative, but it's not humanoid, for example, autonomous vehicle. The driverless car must work in the traffic in collaborative way. Yeah, must avoid other obstacles, must avoid other tasks, must brake when there's danger, and so on. So this is the example of the collaborative. On the other hand, for example, the well-known robot Atlas from Boston Dynamics is not collaborative. It's not purposed for the collaborative work with persons, which is quite also an important feature of lot of features. There is, let's say, even the technical standards for collaborativeness, which defines the collaborativeness very simple, that the robot stops when there is some obstacle, but definitely is not enough. In a real collaboration, the robot must somehow cooperate with the person. Okay, so this is for the big definition. So, some functional attributes of the humanoid robot. There must be sensory motor integration. This means that perception and action of the robot are tightly bound together. The robot must work in a real time. So it must perceive the situation and act directly in the environment without big delay. It should learn, this is an important feature, and also should be able to understand, let's say, the humans. Expressing, let's say, understanding, gestures, speech, emotions, and so on. One important point is close to control. This is, let's say, the terminus technicus, which gives us information that the robot is observed its own action and has, let's say, feedback from this action and adapt based on the result of the action of the most. So therefore, we have this kind of perception action cycle, where the base of the perception is performed action on the environment, and there is a feedback which is again taken into account and action analysis. So, how we will understand the perception? Perception is not pure sensing. Yeah. The inputs from the sensors must be somehow processed with prior knowledge, prior data power, and then with this data, they are somehow transformed to direction. So there is a there are, let's say, the three kinds or three activities which must be performed during the perception. The first is, let's say, the selection what we are see. So even human do not, let's say, everything what is around them. We let's say, narrow our focus to some important points or some important inputs. That's one thing. There is different level of attention which we let's say apply on our environment. The same is for the roads. Then the data should be somehow organized. There should be some kind of identification of the elements which are there by all. And then this sensory information must become interpreted. It must be analyzed, and based on the results, one action is made. So the perception process is not simple. It requires some learning, memory, expectation, and attention. Basically, we can speak that it is transformation of low-level inputs to some high-level organized information. So, therefore, we have some, let's say, action flow, or the perception reasoning action flow, which every autonomous robot must perform. So from sensory inputs to some actionable knowledge that can be used for some activity. We will go step by step through the activities for the task and the So first we have sensors. Of course, the first, the most important sensor for visual perception is camera. Standard camera, RGB, or camera which also measure depth of the objects, RGBT. Can be stereo camera, can be mono camera, can be fisheye, wide angle. Very often, if the robot is used in the outside or big space, the LiDAR, light imaging detector and bandit, is used. So this kind of equipment you see here, which emits the laser light and laser beam, and based on the inputs, the reflected light creates the picture that I Visual perception from camera and LiDAR in many applications is not satisfactory. Basically, we cannot just directly visual input, measure weight, pressure, the kind of forces from the environment. Therefore, we need also other elements which allow the robot to measure such, say, the parameters. And also, we should measure, let's say, the things like, let's say, the motion, angles, let's say, other activities like, for example, the rotation. For this is used inertial measurement unit. I don't know whether many of you know how this element looks like. You should have in your mobile the inertial measurement unit. Basically, you are using it every day. If you turn your mobile, the picture is turned. It's the gyroscope inside the unit. Accelerometers, you basically you are counting your steps during the day. The accelerometer in your mobile is doing this actually for you. I have some examples. IMU, if you want. This is IMU, for example. It is basically a very cheap one using in, let's say, the children robot. Okay, definitely the notice audio. There is very important proprioceptive sensors which are, let's say, in controls of the motors with the joints of the robot. And also they can be sensors on the screen. Basically, sensor provides raw structured and timestamp data, which are needed for the, let's say, the perception that they must be subject to, let's say, the approval processing. Okay. So, from the raw sensory inputs, we have to somehow extract so-called low-level features. These are typically, for example, formats of the picture, lines, edges, let's say the areas with the same color intensity of the same color. I think it would be contour of the pictures. Here is the list of the typical low-level features which are extracted from the raw image. These data are further used for the next processing. But before we go on, we should think how this robot should be put in action. Imagine you are a robot, outdoor smoker. Without electricity, it's just dead iron. Then there is power up, the electricity starting. You are starting, you're booting. You should now orient in the space. You should press the check whether your system is working properly. You should check your position. What's your position? For this, the IMU is very important because basically you cannot check everything, just determine orientation, velocity, external forces which influence you, the ground you are staying on. Everything should be estimated at the beginning of the action. So you have to somehow estimate your internal states, or internal states, and the external states which directly, or external parameters which directly influence your body. This is what, let's say, the robot state estimation should perform. So, the result of this action is continuous, best possible estimate of the robot state. It's estimation because of course, each sensor has some, let's say, the rule or some noise. Therefore, we are every time speaking, probability tennis when we are defining, let's say, the robot state estimation. We have, let's say, the global teacher extraction done. We know how position come out. We can go on with the object and scene recognition. There is a lot of applications which are common also for the standard, let's say, the computer vision, which are applied on the object, on the picture, and on the scene itself. Object recognition focus on, let's say, the unitary objects on this. On the picture, the scene recognition recognize the complete scene. This is typical, let's say, the object recognition camera. This is scene recognition, which is usually used for the autonomous vehicle, if we are outside. So that is, except the object recognition, there is some pose estimation. There can be a spatial map, which is enriched by the labels. This activity, it's, let's say, then we have a step for, let's say, the further processing. When we factor in the touch activities, we can go further and do some, let's say, the segmentation of the scene. The first step is so-called semantic segmentation. If you look on the picture, the persons are identified. Semantic segmentation is usually satisfactory, for example, for autonomous vehicle. The autonomous car doesn't need to know much about the person. There is satisfactory. There are persons, there are cars, there are maps, there are unmovable objects. This type. If we have an application which should, let's say the robot which should communicate with individual persons, then we need so-called instance segmentation. We have to distinguish one person from the other. So it's next step. This is for many applications again satisfactory, but if we would like to move in the from scene, we need parametric segmentation, which also somehow segment the background. There are also, of course, other specs which are possible, some kind of geometric segmentation, identification of the alphabet system, function segmentation. These are the specs which are relevant for computer needs. With performance segmentation, we can go on with semantic mapping and labeling. So we actually can create the model of the world. Semantic mapping goes beyond the direct scene recognition. Scene recognition is recognition what the you or robot directly see. But semantic mapping is creating the, let's say, the internal world. So it needs remembering what was seen and building up the model of the world from the several of continuous observation. So you have to go, for example, to the room on the track, and when the robot goes back, should be able to understand how the overall looks like. Or if, for example, car is moving, mapping the streets, then at the end of the road, when they return into the original place, should be able to create the, let's say, the semantic map of the space. It's definitely not too simple because, of course, the robot will never come to the same place or the same position. Yeah, you never step second time the same mirror. So basically, there is non-trivial task to recognize the same place from different angles or with some changes. After this activity is performed, we should be able to have, let's say, the usual 3D space model of the world around them. Okay, this is the world vision model, which is somehow modeled. But this is usually not enough because we have to also perform some activities in the world. We should be able to perform actions. For this, we need somehow, let's say, the map of what was, let's say, this what was seen with information which are known already. So we should be able to say that, okay, I recognize that, and I should be able to drain it from it. That should be so there must be information which is definitely not included in the picture. Information about this, that this is kind of companion, is not included in the picture. This information is somewhere in the memory of the or in something which is used for, let's say, assigning some kind of affordance to this object. So the robot should be able to answer the questions like, what can I do with this object? Is this object a container? What action to follow? So we had several, let's say, the presentation about ontologies that for our, let's say, purposes. Ontology is just a way how to assign the meaning to perception, yeah, from the very engineering point of view. There are some ontology elements which are assigned. This is, let's say, that kind of structure way how the ontology is performed or defined. But if we would like to define the ontology in natural language, usually some user manual should be satisfactory. Very often it's not trivial task. For example, I have here such thing. Maybe somebody knows it. What is this? Try to define. So you have object, you perceive it perfectly, yeah, but you are missing the ontology. Yeah. So that's the reason why the ontology is important. Yeah. So what for it is? What's the meaning of the object? So actually, with ontology, we should be able to understand the affordances of the object, which was somehow tested. There is, let's say, affordance is basically the set of potential actions which a robot with these abilities is able to perform with the object. That's simply the definition of the affordance. There is several kinds of affordance. Physical, very simple. Graph table, item visit, with table. For example, trust the trade, pouring with the water in, this we understand. But for example, process-oriented affordance for this object may not be known for everybody. So basically, it is putting out the cherry stone from the cherry. Yeah? That is that. So this is just for illustration that it's not trivial task to perform such activity for the robot. There must be something which describes the activity, or the ontology, basically, which must be assigned to the recognized object. And based on all these activities performed, we should come to the actionable knowledge. If I would ask a robot, okay, put all the cherry stones out of the cherries with this tool, the robot must somehow come to the actionable knowledge. Okay, I'm the tool which looks like this. I have to fight it. I have to work with this tool properly. I need to know cherries and so on. So there's a lot of things which must be performed just to be able to perform the task. So the result of the perception in the robotics should lead finally to some actionable knowledge and therefore declaration. Okay, so this was the introduction. Let's dive deeper in the robotic visual perception. Robotic perception is basically a part of the computer vision in general, but there are some specificities which make it more complicated. Okay, a robot definitely needs some kind of special memory, reasoning, and control. The arms, other effectors. The vision must support the manipulation, locomotion, and bonding, which is not so easy if, for example, you are humanoid and when manipulating with the equipment, you just got them by your hand. So your, let's say, the vision is somehow pocket. On the other hand, the computer vision is usually passive. Very often, usually offline sub-image interpretation, and you don't have the problems which the robot was usually by itself. So, robotic perception must in real time, must use the sensor from the robot, is action oriented, and is performed in dynamic environment. The condition for the robotic perception is so-called SLAM, simultaneous location propagation and mapping. Basically, this is used for the robot to create some basic understanding of the environment. So, where I am, so where is my camera position? What is my camera position? Where I am in the environment, what I see. So these are, let's say, this is the basic step of any kind of the robotic visual perception. There are algorithms which are very often used, or some diffusion but basically for your numbering, this activity as a SWAM is important for the navigation, localization, and mapping of the environment. Without this, you cannot assign the task to the robot because he will not be able to perform it. There is quite a lot of problems with perception in dynamic environment because if we have a collaborative robot, we usually want that he is adapted to the moving objects and humans. But this means a lot of problems when, for example, the robot is moving and humans are moving around. If they can in the motion blur, even by the robot, let's say the work, head movement, there is a lot of occlusion in real-time work. If the robot is moving, there is definitely change of the viewpoints, and just to understanding that I am looking to the same object from a different angle, it's very important and task. Very often is the problem with display, foreground and background. Obvious simplification is that objects in the foreground are moving and the background is usually static. In many applications, it is so. Nevertheless, for example, in real traffic, it is not true. So this, let's say, the selection of the importance, or let's say the important object that is the background, is very often about the application. Also, the robot must perform multi-object tracking. Several persons, several cars, several objects. And the map must be adapted very often. Well, this actually is. Usually, there is not enough to have just one sensor, for example, camera. Very often, there is a necessary step which is called sensor fusion, and data from different sensors are fused together for single space. It's a very important task because it can, let's say, solve a lot of problems which are, let's say, occurring continuous in real time. So occlusion of the objects, a loss of signal, different line conditions, for example. If you are coming, or robot is coming from the light room to the dark room, immediately there is a change in the, let's say, the light condition. If there is other sensor, for example, lidar, this it is not impacted by this, it helps out in orientation for our Evox cells. So the redundancy in the sensor fusion is usually very useful for, let's say, the proper navigation and proper task configuration. The robot is moved in 3D space in real world. There is several possible representations or simplification of the real world for the internal world. One of them, one of the most simple and therefore, let's say, very often used is so-called voxel. Voxel is basically the 3D pixel. It's a kind of cube which, let's say, represents a piece of, let's say, video space. There are also other representations, like, for example, octal trees and so on, structured higher and higher trees. But in real-time processing, let's say, we are usually working with voxel. This is the picture which somehow represents the, let's say, spatial recognition of the robot, how it can perceive the world around you in the room, how some of the important objects for the task identified, the other objects are just gray, they could be out. There is quite a lot of let's say, the low-level feature extraction methods. I have, let's say, if you have time, advanced modification which we use in later. But basically, this low-level feature extraction, the requirement is to be performed fast, to be performed, let's say, even with quite a big level of error or noise, but to be performed on the whole picture to allow the, let's say, the full vendor to extract the important information. Based on these inputs, the semantic recognition and mapping is performed. Yeah. So based on this, let's say, the inputs, a robot should somehow learn how to perceive the objects. There is several standard methods for the learning. So there is supervised, unsupervised, self-supervised, reinforcement learning for categories. Oh, you'll be through. Supervised learning in robotics is a standard method. So if you have data set with the labeled data, you can use it, you can train. There is a lot of pre-trained models, which, for example, YOLOs, which can recognize the person's first look. Yeah, so I will say that this is the start. We think it should be very much. The limitation of the supervised learning is usually a lack of data. If we are moving in 3D worlds and if we are using the video, there is not enough label bits, especially if we have observed video. If we have it, we can do a lot, but usually this is something which limits us with training. The second point is that we don't have enough time. It will be simulators with processing capacity, whatever, to train the robot on the real data. So we have lack of data, and even there's enough data, we don't have enough time. It's possible to reuse data. So there is, for example, a way how to save the time, use the pre-trained, let's say the pre-trained models, and also to use other extensions like, for example, self-supervised creation. Another option is unsupervised learning, which can be what we use on the data. We can use some kind of clustering. Very often, this is, for example, used if we have to recognize the same object from different angles. We can use kind of contrastive learning as well. Another option very often used is self-supervised learning, which allows a robot to use the data, which otherwise would be only subject for unsupervised learning, but with small help can be used for the very efficient and let's say the easy task for easy way how to train under the. Let's imagine that we have some videos from the real world and underworld. We would like to teach the robots how to, let's say, understand this environment, how the action should be performed. We don't have local data set, but we don't need it for a lot of learning. For example, we can use the video or video pictures, and we can mask some let's say pixels or voxels on this thing, and we can train the robots to complete back the picture. We can have, for example, video its sequence of the moves, and we can mesh up these things and try to teach the robot or system how to, let's say, build it in for a perfect order. This is the way how the robot can learn, let's say, the facts from the real world, how it can, let's say, reconstruct or let's say, deliver the situation which is, let's say, improbable or impossible from the situation which is correct. Other possibility is to have, let's say, the contrastive learning. That means that we have very simple labels which describe, okay, this is one category, this is another category, and try to, let's say, assign things to the right place. These methods allows, without the big involvement of the human, to teach the robot based on the, let's say, the more as raw data. The result from the, let's say, the 3D representation learning should be that a robot understands how to behave in a real world, what is possible, what is not, how to, for example, grasp the object based on the, let's say, the videos from the other lesson. Reinforcement learning is a possibility which can be used. Okay, in 3D robots, it's very kind of complicated to do the reinforcement learning. Therefore, the reinforcement learning is very often done in simulators. But the issue in reinforcement learning is sample inefficiency. If we would like to teach the robots to grasp the object, in reinforcement learning, if we start with some, let's say, the random set of variables, then we have 10,000 moves just to grasp something. After this amount of moves, the hand is uncalibrated or even damaged. So therefore, we need to use the simulators for using the reinforcement learning. This is one of the, say, the big problem of reinforcement learning. There is a lot of work to be done in this area with increasing the sample efficiency, and it's so-called seed to river transfer, the transfer from simulator to the real world. So there are some, let's say, the standard algorithms which are used, but basically this is the area which needs a lot of research. One of the possibilities how to move forward is to use the kind of reinforcement learning where we really not just consider motivate the robot by realization pattern, because this is very smart motivation, but extend the, let's say, the external motivation by reaching the goal. There is also internal motivation, the robot has kind of boredom and is motivated for performing an action. And let's say in the policy, there is a preference for the unknown objects. So let's say the reward function is rewarded for the activity towards unknown objects. And a robot basically has implemented kind of curiosity or let's say interest for novelty. What can I control? What can I perform? What happens with some actions performed? So this kind of say the curiosity, if implemented, it significantly increase the let's say sample efficiency. This is the one of the way how to let's say the increase the sample efficiency and how to let's say the lead robot education in the right direction in a shorter way than just let's say the mechanical repetition of the activities until I am able to grasp it and will get some result. So perception is not just only the physical perception, but when we are speaking about human robot interaction, there is also a need for perception in the area of let's say the social awareness, means human gaze, posture, facial expression, emotions, and so on. So a robot should be able to, in real time, to interpret the human behavior. This is not a simple task. Definitely, it is things which need much more, say, the research, but some basic, say, the emotions are understandable. A robot should be able to collaborate with person based on their, let's say, the emotions, based on the, let's say, the movement of the hands and so on. Okay. So, one of the areas which are necessary for say the robot moving or actions is visual control of the robot body. So in this case, the robot is itself. So it perceives effectors, and based on the let's say the basic position of the effectors, it performs selection or a correct position or correct direction. So basically, you use camera to navigate the hand or arm. So this is used for the, say, the control of the motion, control of the grasping, and manipulation. We can speak in this case about the visual grasping, visual servoing, for example, that I navigate my hand based on the holistic. Or a robot grasp the object without prior knowledge about its coordinates. The robot is leading its hand to the object. So, challenges and for the research directions, this is quite a list of the challenges in each area that is more speak about. So it's from the motion, the image distortion, and way to stabilization of the reflect. Let's say the solving problem with occlusions, changing scenes, and so on. Generalization, 3D perception, depth estimation. There's a fusion in calculation, sample inefficiency, human posture, and human emotional state. These are basically the areas where in each of these there's some further research necessary. So thank you very much.